Assalamu alaikum guys. My name is Sanjay and today we're going to be solving a chemistry A level paper. This is paper 4, P41, meaning it's a paper 4 and the variant of the component is 1. This is May-June 2025. So as soon as we start solving all the questions, you will see a pattern that I'm going to keep going slow and slow just to ensure that you understand each and every question perfectly. And secondly, for every question, there is obviously supposed to be a background topic, right? Where the question has come from. So for example, if it's a solubility topic, if it's a thermal stability topic, if it's a kinetics, equilibrium, transition metals, group 2, organic chemistry, whatever it is, I'm gonna make sure that I revise that part and then I come on to the question. So instead of just simply solving the paper, you will be also revising the topics in your syllabus. So let's just start with the first question. Bismillahirrahmanirrahim. So the question says that both calcium carbonate and barium carbonate decompose when heated to form a metal oxide and a gas. Write an equation for the thermal decomposition of CaCO3. Now, what is the question telling us? The question is telling us that you have two group 2 metal carbonates. So, why am I saying group 2 metal carbonates? Look at this, calcium and barium. Calcium and barium are examples of group 2 metals. And when chemically combined with a carbonate ion, they become a group 2 metal carbonate. So I have two group 2 metal carbonates which decompose when heated. What does decompose mean? Decompose means breaking down when I provide heat in order to form a metal oxide and a gas. We already know this reaction from our IGCSEs and our AS levels that whenever you have a group 2 metal carbonate, you thermally decompose it, you form that metal oxide and carbon dioxide. So let's say if you have barium carbonate thermally decomposes or thermally breaks down into barium oxide plus carbon dioxide gas. Let's try another one. Let's take calcium carbonate. Calcium carbonate again thermally decomposes into calcium oxide plus carbon dioxide. So if the question is write an equation, yeah, we have already solved this. Write an equation for the thermal decomposition of calcium carbonate. So it's basically calcium carbonate simply decomposing to form calcium oxide plus carbon dioxide. Nothing really to understand here. It's basically just a reaction which you have to rote learn. Some of these reactions in A level chemistry are those which you have to remember by heart, as in the pattern that if you have a group 2 metal carbonate, you metal oxide and nitrogen. If you have, let's say, a hydroxide or two hydroxides, then what is the trend in their solubilities? If you have a nitrate, then what does it decompose into? So these patterns are what you have to remember. Now, question number 2. Look at the command word of the question, state. The first thing you need to understand is what does state mean? State which of blah 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 blah. It's a one word answer. So when it says state which of calcium carbonate and barium carbonate decomposes at a lower temperature, it is simply asking us to write down the name of the compound which decomposes at a lower temperature. What is this question making us do? It's making us compare that which group 2 metal carbonate is breaking down at a lower temperature. This is a question from the thermal stability of group 2 carbonates. Now, how did I just figure that out? How is it thermal stability? Well, it's simple. Think about it. What do we mean by something being thermally stable? Let's say I have a substance, just take any random substance, and to that substance, you give a very, very large amount of heat. You increase the temperature by a great amount, let's say 200 degrees Celsius, and you're giving lots and lots of heat. Because of that heat, the substance finally decomposes. The substance was not decomposing at a lower heat, but as soon as you gave it lots and lots of heat, it finally started to decompose. What does that tell you? That the substance decomposes at very high temperatures. It is extremely thermally stable. It is extremely stable if heat is provided to it. So, if I ask you this, what do we mean by being more thermally stable? It means that even if you provide lots of heat energy to it, it's not going to break down or decompose easily. Now, second question. What do we call having less thermal stability? It means that even if you give it a small amount of heat, it's going to decompose really, really quickly. This is exactly what the question is asking us, right? Which one is decomposing at a lower temperature? Meaning, if I give a small amount of heat, which one is going to decompose? AKA, which of these two group 2 metal carbonates have a lower thermal stability? Now, you guys should learn this trend by now when you were studying your syllabus that when we talk about the trend of group 2 metal carbonates, the trend is that the thermal stability of group 2 metal carbonates increases down the group. What do I mean by down the group? It means that as you keep going down group 2, the thermal stability keeps increasing. So let's say if you're comparing beryllium carbonate and magnesium carbonate, magnesium carbonate is going to thermally decompose at a greater temperature because it is more thermally stable. How do I know that? Thermal stability increases down the group. Now let's say you're comparing calcium carbonate and barium carbonate, which was our question. Thermal stability increases down the group. So which one is going to be more thermally stable? Barium carbonate. Which one is going to be less thermally stable? Calcium carbonate. So if calcium carbonate is less thermally stable, doesn't that mean that it's going to decompose at a lower temperature? Yes. So calcium carbonate is our answer right here. But we still haven't figured out what's the explanation as to why this is less thermally stable compared to barium carbonate. What most students do is they just write down the trend. Their trend is that thermal stability increases down the group. That's not the explanation. That's the pattern or that's the trick for you to find out the answer. A trend is simply a trick. It's not explaining why one compound is less thermally stable than the other. There is a proper scientific explanation to it. Let's just understand this. Now, let's compare a calcium ion and a barium ion. If I can ask you this, which one of these two ions has a bigger size? I'm going to go back to the periodic table. Calcium or barium? Most of you will say barium, and that's right because when we go down the group, the size of the ion increases. This is AS chemistry. If you go down the group, the size of the ion increases. So barium ion is larger in size, and a calcium ion is smaller in size. Now, let me just give an example of what is actually happening when you have a group 2 metal ion and a carbonate ion. What's actually happening between them? So, let's take an example of a calcium ion. A calcium ion is Ca2 plus, and a carbonate ion is CO3 2 minus. So, basically, it's going to be like this C double bond O. Let me just erase this. C double bond O. This is the second O, and then this is the third O. We have a minus sign right here. Now look at this. What are bonds actually made of? Bonds are simply shared pair of electrons, right? For example, how did this bond form? Oxygen donated one, or not donated, sorry, shared one electron, and then this carbon shared one electron to form this pair of electrons, aka the bond. So, bond is simply a region wherein we have the pair of electrons being shared between these two atoms. Look at this. It's a positively charged ion. Positive, negative. Electrons are negative, right? When you bring positive close to the negatively charged electrons, what's going to happen? They're going to be attracted to each other. When they become attracted to each other, it will cause this bond right here to increase in size, to increase in length. Why? These electrons in the bond, they are being attracted to this positively charged metal ion. So it's going to pull it towards it. These electrons are going to be pulled towards the calcium ion. So the size first it was like this, Now it's going to be something like this. Simply speaking, the bond length is going to become larger. Why? Because of the positively charged metal ion. Now, you do know what just happened, right? Positively charged metal ion pulling on these negatively charged electrons. This is called the polarizing power of the metal ion. What is it called? The polarizing power of the metal ion. When we talk about polarizing, polarizing simply means attracting something towards oneself. So, this positively charged metal ion is attracting these electrons towards itself. It's polarizing the carbonate ion. Why? Because it has the power to do so. So, this metal ion has some sort of a polarizing power, because of which, because of which, the carbonate ion is polarized. If the calcium ion is applying a polarizing power, the carbonate ion is going to be polarized. Now, what does polarize means? Polarize simply means that the bond length, in this case, what does polarize means? The bond length between the carbon and the oxygen is increasing. Now, think about it. If the bond length is increasing, what's happening to the bond energy? It's decreasing. So the bond energy, short form B dot E, is decreasing. What's going to be more difficult to break? Is it a smaller bond or a bigger bond length? A, a smaller bond, right? Lesser the bond length, greater the bond energy. We learned this in AS chemistry that bond length is inversely proportional to bond energy. The smaller length of a bond you have, the greater the energy required to break it. However, if you have a bond which is of a bigger length, then smaller amount of energy is required to break it. So, if the bond energy is decreasing, it means that the bond will break easily, even if I provide a lower temperature. It's gonna break easily even if I provide a lower temperature, meaning that if I provide a small amount of heat, it's still gonna break because of the high polarizing power of the calcium ion. So because it has a very high polarizing power, the carbonate ion is gonna be really, really polarized, which means that it's gonna be broken very, very easily, aka lesser thermal stability. Let's compare this to what happens between a barium ion and a carbonate ion. And now you'll understand in a second as to why earlier I was looking at their sizes. So you have a barium ion, and then the same size as earlier, you have the carbonate ion. Now, look at this. Compare the barium ion with the calcium ion. Do both of these ions have the same charge? Yes, they do. 2 plus and 2 plus. But here's a very important question. Both of these ions have the same charge. But in which case is the charge more concentrated? Is the charge, in which case, is the charge more spread over a smaller region? You will say calcium. Because there's a very small space, it's a very small ion, and it's a 2 plus charge, it is very concentrated. But now look at this. It's the same 2 plus charge, but now it is spread over a larger amount. So we will call this a lesser concentrated charge. Now, let me ask you this. Which ion do you think is going to cause this carbon oxygen bond to be pulled more? Or in the case of calcium or helium, most of you would say calcium because it's a concentrated ion or an ion which has a concentrated charge of 2 plus. So it's going to attract the negatively charged electrons easily, meaning the carbon oxygen bond is going to be pulled a lot more, so it's going to increase a lot more inside. You compare that to a barium ion. In a barium ion, it's the same 2 plus charge, but this 2 plus charge is spread over a larger amount. This charge is going to have a lesser strength to pull this bond. The bond is going to be pulled, I agree with that, but it's going to be pulled lesser. So basically just this much. Look at the amount by which the bond increase here, the bond length increase here and here. It's going to be a lesser increase or a lesser change in the second case. So now, which bond length do you think is higher? Number one or number two?
Number one, because the bond length here is higher, the bond energy here is lesser, meaning this bond is going to break more easily even if you provide a lower temperature. But because here the bond length is lesser, so the bond energy is higher, which means that this carbonate ion is more thermally stable. This is basically the entire topic of thermal stability of group 2 carbonates. Let me just quickly revise this. You have two ions, and two examples you're dealing with, a calcium ion and a barium ion. Even though both of these ions have the same charge, a calcium ion has a greater polarizing power. So think of polarizing power as the ability to be able to pull the electrons in the carbonate ion. It has a greater polarizing power. Why? Because the same 2 plus charge is spread over a smaller amount. It's concentrated, the charge is concentrated in this calcium ion. So you can think of the charge having more strength. It's more strong to pull this bond more. But if you compare this to barium, the charge is the same 2 plus charge, but it's spread over a larger amount. So meaning it's going to be weak, the charge is going to be weaker, it's going to have lesser strength of pulling this pair of electrons. So the bond length is going to be higher in the first case compared to the second. The bond energy is going to be lower, here is going to be higher. So lower thermal stability, higher thermal stability. Let's write all of this down in our explanation. So calcium carbonate, and why is that? Because Ca2 plus ion has a bigger ionic radius, which is what we talked about. It has a bigger size. Now, if it has a bigger ionic radius, what effect does that make? This means it has a greater polarizing power. Now, you don't need to talk about the same 2 plus charge in both cases, and then in the first case, the charge is less spread, in the second case, it is more spread. This is all for your explanation. What you simply need to write down is a summary that this means that it has a greater polarizing power. And because a calcium ion has a greater polarizing power, meaning the carbonate ion is going to be more polarized, or polarization is going to be higher in calcium carbonate. So the carbonate ion is going to be more polarized by the calcium ion. Hence, the calcium carbonate is less thermally stable. Again, see, in this explanation, I did not talk about bond length, I did not talk about bond energy, because both of these things come under polarization. I did not talk about the charge being less spread and the charge being more spread in the metal ions. Why? Because that comes under polarizing power. This is the importance of keywords. If in the exam you know the information, you know how things work, but you don't know the keywords, this is what you're going to miss out on. Examiners write this in the marking scheme as bold, right? You must have seen this sometimes. Writing it in bold means that if you have not written this word, they will not give you the mark corresponding to this word right here. So you need to include the words, keywords. So polarizing power, greater polarizing power, which means that the carbonate ion is going to be more polarized, hence the calcium carbonate is less thermally stable. And just one more thing you need to remember, the metal ions, whenever you talk about metal ions, let's say calcium ion and barium ion, you talk about polarizing power. Whenever you talk about the anions or the non-metal ions, you talk about the polarization. There's a difference between polarizing power and polarization. So that's all about thermal stability of group 2 carbonates. You can use the exact same definition and explanation for thermal stability of group 2 nitrates. Just replace the carbonates with nitrates. It's the exact same explanation. So those are our 3 marks right here. Now again, I know it's been a long time and I've just kept on explaining these 3 marks, but I don't want to solve it faster. I'm not on a time crunch. I just need to make sure you guys understand the entire thing perfectly so that you don't get it wrong in the next time you solve this question in any of the other papers.
So we have calcium oxide, which is CaO. Now, CaO reacts with water in order to form compound A. Then we have another compound, which is barium oxide, which again reacts with water to form compound B. Now, what similarity can you see between these two compounds? We understand that these are both group 2 oxides. Look at this, calcium and barium, both of these are group 2 metals. And because they have an oxygen next to them, this is called an oxide. So, calcium oxide, barium oxide, reacting with water to form compound A and B, respectively. Identify compound A. Now, you need to remember this when it comes to calciums or for example, group 2 metals reacting with water or group 2 metal oxides reacting with water. You need to remember this. Reaction number one. What you need to remember? If you have a metal, so for example, let's say you have a group 2 metal, and a group 2 metal or a group 1 metal is reacting with water, it will produce a group 1 or group 2, whatever metal you are using, it will produce the hydroxide as well as a hydrogen. So let's say, for example, you're taking sodium. So when you have sodium, again metal in a solid form, and then when you react it with water, what is this going to produce? We learned this in IGCSE that the sodium metal dissolves in water, fizzes rapidly. Remember all of those observations which you can see that sodium metal fizzes rapidly, rubidium causes a fire, and all of that stuff. So sodium plus water forms sodium hydroxide, which is NaOH plus hydrogen gas. Obviously, you can balance this chemical equation, but this is going to be all of the reactants and all of the products. The same thing applies for group 2 metals. Let's say if you have calcium, calcium plus water is going to give calcium hydroxide, but this time it's going to be CaOH twice plus hydrogen. If you're confused on why is it NaOH when we are using Na, but why is it CaOH twice when we are using Ca? The problem is, or the process which we use in order to find out the formula of an ionic compound is called crisscross. How does crisscross work? This is really basic, just clearing this. How does crisscross work? You write the positively charged metal ion on one side, negatively charged non-metal ion on the other side. You write the charges of the ions below them. So calcium has a charge of 2 plus, hydroxide has a charge of 2 minus. Step number 2, erase the charges. Step number 3, crisscross them. So Ca pairs with 1, hydroxide or OH pairs with 2. So Ca1 is just Ca, this becomes CaOH twice, or calcium hydroxide and plus hydrogen because calcium is reacting with water. Reaction number one. What's reaction number two? Reaction number two is when it's not the metal, but this time it's the metal oxide which is reacting with water. So calcium oxide reacting with water is simply going to make calcium hydroxide. That's it. There is gonna be no hydrogen produced. You guys need to remember this. No hydrogen is gonna be produced when you have a metal oxide reacting with water. But if you have a metal reacting with water, you make the metal hydroxide plus the hydrogen gas. So calcium oxide reacts with water to form compound A. What's compound A? Calcium hydroxide. You can either write the name or you can just write the formula CaOH twice. Question number two. Explain why calcium hydroxide is less soluble than barium hydroxide. So what topic is this question from? This is from the solubility of hydroxides. Now, for those of you who do not understand solubility of hydroxides, let me explain this in a bit detail. For those of you who do understand it, just skip to the part where I'm writing down the answer. For those of you who don't, listen closely. So, what are we going to discuss right now? The differences or the trend in the solubility of group 2 metal hydroxides. So, let's take calcium hydroxide and then let's take what was the other one in the question? The other one in the question was barium hydroxide. All right. So let's take calcium hydroxide and barium hydroxide. CaOH twice and BaOH twice. First question. Which metal comes first when you are reading group 2 in the periodic table from top to bottom? When you are reading this from top to bottom, which metal comes first? Calcium. Barium comes after calcium. The trend that you need to remember, and we'll discuss the reason behind it, but first you need to remember the trend. Solubility of group 2 hydroxides increases down the group. This is the first thing that you have to remember. Solubility of group 2 hydroxides increases down the group. What does this mean? This means that barium hydroxide is going to be more soluble compared to calcium hydroxide. How do we know that? Solubility increases down the group. So let me write this down. Solubility of group 2 hydroxides increases down the group. Now let's understand why does this actually happen? Well, whenever you talk about solubility, right? Whenever you talk about solubility, you have to talk about something called enthalpy change of solution. What is enthalpy? Enthalpy is simply energy change. Enthalpy change of solution, you would have learned this in chemical energetics, is the enthalpy change or the energy change whenever 1 mole of a substance is dissolved in excess of water to form a dilute solution. So let's say I have 1 mole of calcium oxide. When I dissolve that 1 mole of calcium oxide in excess of water, so let's say I have a container, it has way too much of water inside of it. I put 1 mole calcium oxide. This dissolves in excess water and it forms calcium hydroxide. The energy that is released because of this dissolving process is called enthalpy change of solution. That's the first thing that you need to understand. Now let's talk about the second thing which we need to know. If our enthalpy change of solution is negative or small positive, so let's say if it's minus 10 joules, kilojoules per mole, or minus 20 kilojoules per mole, or zero point 0.1 kilojoules per mole. So what are the options that we have? If the enthalpy change of solution is negative or small positive. So it's positive, yes, but it's really, really, it's a very, very small value, a small magnitude. So negative or small positive, it means that the substance which you dissolved, so in our case, it was calcium oxide which we dissolved, is soluble. And then opposite to that, if the enthalpy change of solution is high positive, so let's say plus 20 kilojoule per mole, plus 30 kilojoule per mole. Is this small positive or big positive? plus 20 or plus 30, it's big positive. So if it's positive, then the substance, whatever substance you tried to dissolve in water, is insoluble in water. Right. These are the 2 points. Point number three. Whenever we talk about enthalpy change of solution, remember the Hess cycle which you guys learned about in chemical energetics? From that Hess cycle, we made or we formed a chemical equation. Obviously, I'm not going to go into the Hess cycle now, it's going to be really, really long. But just understand that when we performed the Hess cycle, we created a chemical formula. And that was enthalpy change of solution is equal to lattice enthalpy of dissociation plus hydration enthalpy or enthalpy change of hydration. Now, I know what you guys are thinking. You guys have learned about lattice enthalpy, but you haven't learned about lattice enthalpy of dissociation. Some of you might have, some of you might have not. Well, listen to this. Whatever you have learnt about lattice enthalpy, just reverse that. That's lattice enthalpy of dissociation. So, what have you learned about lattice enthalpy? When gaseous ions react together to form 1 mole of ionic solid, the energy released is called lattice enthalpy. So, let's say if you have a sodium ion, which is again gaseous, and you have a chloride ion, which is gaseous, they react together to form 1 mole of ionic solid, which is in this case NaCl. So, gaseous ions reacting together to form 1 mole of ionic solid. It's called lattice enthalpy. So because bond forming occurs, and what's bond forming? Exothermic or endothermic? Bond forming is exothermic. Okay. Now what's the opposite? Meaning if I have to go from an ionic solid to the ions, it's the opposite. This is called lattice enthalpy of dissociation. The ionic compound is dissociating. So in the SS cycle, basically, we just draw the reverse arrow for what we usually draw for lattice enthalpy. So enthalpy change of solution is lattice enthalpy of dissociation plus enthalpy change of hydration. Now, if lattice enthalpy, what you guys learned in your syllabus, if it's negative, right, bond forming, then shouldn't lattice enthalpy of dissociation, the reverse, be positive? It will be. And obviously, enthalpy change of hydration is bond forming. This is separate. This is negative. Let's take an example. Let's say I'm going to write some random values for lattice enthalpy of dissociation. Ignore the spelling for a second. Right here, I'm going to write some random values for lattice enthalpy of dissociation. And here, I'm going to write some random values for the enthalpy change of hydration. So let's say plus 800 minus 800. Let's take plus 700 minus 750. And I'm going to explain these values in a second. Please do not remember these values. It's just an example. Minus 700 plus 500 minus 650. I want you to calculate the enthalpy change of solution in each case. How will you calculate? Enthalpy change of solution is this plus this. 800 plus minus 800. What's 800 plus minus 800? 0. So here the enthalpy change of solution is 0. What about this one? 700 plus minus 750. Plus into minus is minus. So 700 minus 750 is minus 50. Then after that, minus 100. After that, minus 150. Enthalpy change of solution was first small positive, right? Meaning this is soluble. And then it became negative, more negative, more negative. What is this? Is the solubility increasing or decreasing? The solubility is increasing. If your enthalpy change of solution value becomes more and more and more negative, what does that tell you? That the solubility of that substance which you put in the water is increasing. Now, look at the lattice enthalpy of dissociation values. How do they change? And look at the hydration values. How do they change? Minus 100, minus 100, minus 100. Plus 50, plus 50, plus 50. Both values are decreasing, right? Ignore the minus sign for a second. If you take into account of the minus sign here, you'd be like, oh, minus 800 to minus 750. Shouldn't this be plus 50? Then why am I saying minus 50? Just ignore the signs for a second. If you ignore it for a second, just look at the numbers. It's decreasing, right? By 50.
and this is decreasing by 100. Which of these two is decreasing more rapidly? You would say, of course, it's this one. This is decreasing more rapidly, 100 each time compared to 50 each time. Correct. The one which decreases more rapidly, this is our dominant factor. Now, imagine this. What is this? This is the energy required to break that ionic solid which is formed back into its gaseous ions, right? So let's say if you have Na plus gas plus Cl minus gas, the forward reaction is lattice enthalpy. But the backward reaction is lattice enthalpy of dissociation. So what is this? You're breaking the ionic solid into its ions. Bond breaking. Bond breaking is endothermic. That's why positive. Now, every single time, look at this. Lesser and lesser energy is required to break the bond. If lesser and lesser energy is required to break the bond, ask yourself this. Isn't it going to be easier to break the bond because you're taking lesser energy each time, right? So breaking the bond becomes easier every single time. If breaking the bond becomes easier, it means solubility is increasing. This is what we need to understand. Let me revise this entire thing again. I put down some values for lattice enthalpy of dissociation and hydration enthalpy. This was decreasing, this was also decreasing, but this was decreasing at a more rapid rate. This is our dominant factor. Now, imagine this. These are the energies required to break the bonds in NaCl so that it goes back into Na plus and Cl minus, basically the backward reaction, right? That's lattice enthalpy of dissociation. If you require lesser and lesser energy to break the bond, it means it's getting easier for you to break the bond. If it's getting easier, it means that it's becoming more and more soluble. The solubility is increasing. Now, what if it's the opposite in any other case? If it's the opposite, meaning what if hydration enthalpy decreases more rapidly? Then it's the opposite answer, that solubility is decreasing. Simple as that. If lattice enthalpy of dissociation is the dominant factor, solubility is increasing. If hydration enthalpy decreases more rapidly, meaning this is the dominant factor, solubility is decreasing. So let me write down the answer here. Why is A less soluble than B? First answer, A is less soluble, meaning calcium hydroxide is less soluble than barium hydroxide. Why? So talk about the enthalpy change of solution values. In which, so suppose this was for calcium hydroxide and suppose this was for barium hydroxide. In which case is the enthalpy change of solution value more exothermic or more negative? In the case of barium hydroxide, and remember, more negative enthalpy change of solution value means more solubility. The more negative it becomes, the more soluble it becomes. Because remember, if enthalpy change of solution is negative, it means it is soluble. If it is more negative, it is more soluble. If it's less negative, or in other words, positive, it is insoluble. So if this is becoming more negative, means solubility is increasing. So for your first point needs to be about enthalpy change of solution. So you're going to write down that the enthalpy change of solution is less exothermic, or you could say less negative for A compared to B. Point number one. Point number two. In both cases, the lattice enthalpy and the enthalpy change of hydration, which is what we talked about, that lattice enthalpy and enthalpy change of hydration decrease, but lattice enthalpy decreases more rapidly, or you could say becomes exothermic more rapidly. Look at this. If this is decreasing, isn't the value becoming more and more and more negative? So we can say it's becoming more negative rapidly or more exothermic rapidly, or decreases, negative, exothermic, it's the same thing. So decreases more rapidly. That is it. So enthalpy change of solution is less exothermic for calcium oxide compared to barium oxide. Number two, the enthalpy change, or sorry, the lattice enthalpy is more, or you could say that the lattice enthalpy and the enthalpy change of hydration both decrease, but because the lattice enthalpy decreases more rapidly, the solubility trend becomes that the solubility increases down the road. Right, just one more thing. Notice how I talked about lattice enthalpy of dissociation here, but I just wrote down lat or lattice. I did not write down the whole thing dissociation because the disassociation part is just for your understanding. This is not in the syllabus. You're just going to write down lattice enthalpy and not lattice enthalpy of disassociation in your answer. Again, there is nothing wrong with writing it down, but because it's not in the syllabus, you're not going to find it in the marking scheme. So when they write lattice enthalpy in this answer, what they mean is lattice enthalpy of disassociation. It's just that they do not write it down. Right. Let's go to the next question. This is obviously reaction kinetics. Let's see what this question is asking us. Three experiments are carried out, and the experiments which are carried out are used to investigate the reaction of NO, nitrogen monoxide, with chlorine. All right. They give us the balanced equation. Perfect. Rate equation for this reaction is shown under the conditions used in experiments 1 and 2. So they're saying that they carried out two experiments, and under this condition used, the value of K is 26.4. Now, what was K right here? K was the constant used in this case, right? So, meaning that no matter how many experiments you conduct, your rate constant needs to be the same value, obviously, because the constant word literally means remaining the same, meaning in 1 and 2, this value remains the same, which is 26.4. The rate of the reaction is measured in mole per decimeter cube per second. We know that. State the units of K. Okay, how do we know this? That the rate is measured in mole per decimeter cube per second? Because the simple formula for rate of a reaction is the change in the concentration of the products or the change in the concentration of reactants divided by time. What's the unit used for concentration of something, of a substance? Mole per decimeter cube. And for time, second. So this becomes mole dm minus 3 s minus 1. This is what it says. So they told us that the rate of reaction is in this, state the units of K. All you have to do is, in this particular chemical equation, just make K the subject of the formula. So K becomes rate divided by NO squared multiplied by Cl2. Now, what does squared mean? Squared means that it's basically, you can think of it as two NO brackets, right? Obviously, I know that this means the coefficient which is used. So the coefficient here, this is the order or the power of the reactants, but in mathematically, you can just consider it as two NO brackets. Every single bracket means mole dm minus 3. So two brackets means two times we're going to write down mole dm minus 3. So two times here and one time here. So in total, we're going to write down mole dm minus 3 three times. That's our denominator. So mole dm minus 3 times mole dm minus 3 times mole dm minus 3. Just join them together. What's it going to be? It's going to become mole 1, 2, 3. So mole to the power 3. dm minus 3 minus 3 minus 3 is minus 9. Basic laws of indices. Bases are the same. Powers get added. So minus 9. So this entire thing becomes mole 3 dm minus 9. And what does rate of reaction become? It becomes mole dm minus 3 s minus 1. The question already told us this. Now all you have to do is you just have to cancel out the existing or the common values. So if there's 1 mole here, this 3 gets cut down to a 2. If you have a dm minus 3 here, this gets cut down to a minus 6. What are you left with? You're left with s minus 1 divided by mole squared dm minus 6. Bring the mole squared from the denominator into the numerator, what's it going to be? It's going to become mole minus 2. And this dm minus 6, the power is going to flip. It's become dm 6. So this is going to be mole minus 2, dm6, and s minus 1 as it is. So basically what I'm saying is, let me just write this down again. Mole 2 dm minus 6. Whenever you shift something from the denominator to the numerator, the power sign switches. So if this is positive 2, this becomes negative 2. If this is negative 6, this becomes positive 6. And this is already in the numerator, so we do not change the sign for the second. Right. Question number 2. In experiment number 1, the initial concentrations of NO and Cl2 are equal. Okay. The initial rate of the reaction, okay, in experiment 1 is this. So when you mixed some concentration, they haven't given us what, but they told us that these two are equal. So when you mix equal concentrations of NO and Cl2 and you react them together, the initial rate, the starting rate of the reaction in experiment 1 is this. Calculate the initial concentration of NO. Show your work. So we're going to use the same thing. Let's see what all do we have in this particular equation. Do we have the rate? Yes, we do have the rate. Do we have the K value? Yes, we do have the K value. Do we have the NO and the Cl2 concentration? Actually, that's what they're asking us for. Okay, let's see how we're gonna solve this. Let me first write down the things we already know. So we know the rate, 2.57 times 10 to the power minus 6, just writing the rate value in place of rate. And what I'm going to do is I'm going to bring the k value to the denominator just to clean up the equation, just to make the equation shorter. So divide by 26.4 is equal to concentration of NO squared multiplied by concentration of Cl2. Okay. Now what was the question? Calculate this. Do we know the concentration of Cl2? No. Do we know the concentration of NO? That's the question. So obviously we don't. But what we do know is these concentrations are equal to each other. So let's just for a second say that the concentration of Cl2, let's take this as X. If the concentration of Cl2 is X, what's going to be the concentration of NO? Also X. So now what do we have here? We have X squared multiplied with X. What's that? X cubed. So I'm going to erase this entire thing and I'm just going to write X cubed. This is X cubed. Again, if you didn't understand this, let me repeat myself. The concentration of Cl2, you don't know that. Just assume this to be X. And when they told you both these concentrations are equal, treat this also as X. X squared times X is X cubed. All you have to do is just take the cube to the other side to make this cube root like this. So you have the cube root of 2.57 times 10 power minus 6 divided by 26.4. So the answer is going to be around 4.60 times 10 power minus 3. Obviously, I don't have a calculator around me, so I'm just writing the answer as in the marking scheme, but I'm just using the marking scheme to get the answers because I don't want to waste time using a calculator. But this is the exact method that you guys are going to use. You have the rate here, you divide that by the k value, so you bring the k value to the denominator, and then you just cube root it because x was cube on the other side of the equation. Right, in experiment number 2, the initial concentration which we took for NO and Cl2, they are both 10 times greater than the initial concentrations used in experiment 1. So this is the concentration we used for NO, right? And when they said that NO and Cl2 are equal in experiment 1, this is what we use for NO, this is what we use for Cl2 in experiment 1. Now what are they saying? They're telling us that in experiment 2, the concentrations of this and this are both 10x, they're 10 times greater. Okay, calculate the initial rate of the reaction in experiment 2. Now there is a long method to this and there's a shorter method to this. Let's first do the boring, classical, wrong method. Sorry, not wrong method, long method. Just use this chemical equation right here. So rate is equal to K multiplied by NO squared multiplied by Cl2. So if they're asking us for the rate,
You write down the K value, which is 26.4, multiplied by concentration of NO. So it's 10 times of this. So basically, this is going to be 46 times 10 power minus 3. Let me just check. So 4.6 means 1, 2, 3. So this is going to be 0.0046. So 10 times means 0.046, which means 4.6 times 10 power minus 2. Yeah, sorry. 4.6 times 10 power minus 2. Basically, just remove this 3 and just add a 2 here. So 4.6 times 10 power minus 2. Now, look at this, right? NO is 4.6 times 10 power minus 2 squared times Cl2, which is also 4.6 times 10 power minus 2. So can't we just write it as this cubed? It's just square and this, right? These two are the same thing. Bases are the same. When you're multiplying, you add the brackets together. So let me just rephrase myself. The concentration of NO is 4.6 times 10 power minus 2. This is the same as the concentration of Cl2. So instead of writing 4.6 times 10 power minus 2 squared times 4.6 times 10 power minus 2 again, just write it together as cubed. So you just have to solve it, and then the answer is going to be 2.57 times 10 power minus 3. 2.57 times 10 power minus 3. Or the shorter method, just look at the change that is happening. Look at this equation right here. This is, let's call this x cubed. And you had the rate here, and this was equal to k multiplied by x cubed, right? This and this are the same, so I just joined them together to say x cubed. In the next question, what did they do? They just multiplied this by 10. So now all you have to do is, if this is multiplied by 10, what would this be multiplied by? This is all you have to do. But again, if you're still not sure with this second method, you're still doubtful, just use the classical method. It's a bit longer, but it's going to get you to the right answer. Right. Part B. Experiment 3, okay, new experiment, uses a large excess of nitrogen monoxide. The initial concentration of Cl2 is this much. The graph of Cl2 concentration against time shows that the reaction has a constant half-life. Explain this observation. Okay, so how you can explain this? Well, first we need to understand this. What were the reactants used in our chemical equation? NO and Cl2. Okay, so NO and Cl2. They told us the concentration for Cl2, the initial obviously, and they said that NO is being used as large excess. This is a very, very special word, and you need to understand what does this mean. When they use the word large excess, they're trying to tell you that the concentration of NO is going to change, obviously, right? If NO is a reactant in the chemical equation, it's going to react. The concentration of NO will change. But because it's used in large excess, the concentration change is going to be negligible. If you have a chemical reaction that's using 10 grams of water or 10 ml of water, and for this reaction you use 10 liters of water, you have 10 liters of water out of which 10 grams is going to be used. Is it going to make any difference, any noticeable difference on the total amount of water remaining at the end? No, right? It's 10 liters versus just 10 grams. It's basically nothing. This is why we say that the when you use large excess, when you're using an excess of something, the change in their concentration, delta stands for change in the concentration is negligible. Negligible means that you do not take it into account. You do not worry about it. So you simply say, okay, NO concentration does not change. Now, many of you would be like, why are we saying it does not change? It is changing. I agree, it is changing. But because we're using a large excess, is the change visible? Is the change noticeable? No. It's so, so small that you don't even consider it. That it's really, really small, forget about it. Yes, that's actually what we do. So the concentration we write down that it does not change. Now, if the concentration does not change, look at the rate equation. So you cancel this out. Anything that is not changing does not belong in the rate equation.
So you cancel this out. What's the overall order of reaction? The overall order of reaction now is simply 1. Whenever the overall order of reaction is 1, the reaction is going to have a constant half-life. Whenever the reaction is first order or overall order is 1, the reaction will always have a constant half-life, meaning the half-life, the first half-life of the reaction is going to be equal to the second half-life, which is going to be equal to the third half-life, the fourth, the fifth, and so on. The half-lives, consecutive half-lives, are going to be constant. When the order of reaction is 1. How is the order of reaction 1? Isn't it 3 here? Yes. But we cancelled this out. How did we cancel this out? We took a large excess, meaning the change in the concentration of NO no longer matters to us. So we write down that the overall order of reaction is equal to 1 since the concentration, you could just write square brackets to say the word concentration of NO does not change. Or you could also write this, that the change in the concentration of NO is negligible. NO is nitrogen monoxide. You could write this, that the concentration does not change. Or if you want to be extra sure, just write that the change in the concentration of nitrogen monoxide is negligible. Part 2. Under the conditions used in experiment number 3, the value of the rate constant is 105.6. So they used some conditions and then they found out that the rate constant, the K value, is 105.6. Show that the half-life of Cl2 is this much under these conditions. This is a sort of a question where if you don't know the formula, you're not going to solve it. You need to remember the formula. What's the formula? The formula relates half-life with the rate constant, and it says that the half-life for those chemical reactions wherein the order of reaction is 1. So again, you can, the formula which I'm going to write right now, you're going to only use it when the order of reaction, the overall order, is equal to 1, just like in this case. So because the overall order of reaction is 1, we can use this, that the half-life is equal to K divided by 0.693. Now, you have the K value, 105.6. You have the you have the 0.693. That's the part of the formula. So the answer becomes 6.56 times 10 power minus 3. It's going to be a bit off because normally we just use ln2. But some teachers just teach ln2. I like to teach this because this is easier to remember. And you might make some mistakes putting this into the calculator. So it's just easier to remember 0.693. So 6.56 times 10 power minus 3 seconds. Right. Right. Question number 2. Calculate the time taken in seconds, okay, for the concentration of chlorine to fall to this much in experiment number 3. Okay. Now, I'm going to give you a trick right here, yeah? Just make sure you remember this in detail. Whenever you come across a question wherein it says how much time it takes for the concentration to fall to this, from this, and this is immediately after the half-life question, you need to remember that it needs to be related to the half-life. Now, what is the half-life here? 6.56 times 10 power minus 3. Meaning, in this much amount of time, the concentration of chlorine is going to half or divided by 2. Let's keep dividing the concentration of chlorine by 2 to see how many half-lives does it take to go from this to this. So you have 2 times 10 to the power minus 4. Pick up your calculators. 2 times 10 to the power minus 4 divided by 2. What's the answer? 1 times 10 power minus 4. Now divide by 2 again. Let me just do it also. So 2 times 10 power minus 4 divided by 2. First time I got 1 times 10 power minus 4 divided by 2 again. 5 times 10 power minus 5 divided by 2 again. 2.5 times 10 power minus 5 and divide by 2 one more time. It's going to be 1.25 times 10 power minus 5. Did we reach our goal? Yes, we did. So what does this tell you? It tells you that whenever this question of how much time will it take for the concentration to fall from A to B is after a half-life question, you have to keep dividing the initial concentration by 2 and see how many half-lives does it take. So here's our first half-life, second half-life, third half-life, fourth half-life. What is each half-life equal to? 6.56 times 10 power minus 3. So 6.56 times 10 power minus 3 multiplied by 4. Let me write this down. 6.56 times 10 power minus 3 multiplied by 4. That is equal to 0.0264. So it's going to be 0.02. Yeah, we can just keep it at 0.026. Right, part C. We have sulfur dioxide, which reacts very slowly with oxygen in the atmosphere, forming sulfur. Right, part C. We have sulfur dioxide, which reacts very slowly with oxygen in the atmosphere, forming sulfur trioxide, SO3. This reaction is much faster in the presence of NO, or nitrogen monoxide. If you're confused, where did you learn this? You learned this in AS,
wherein, remember the chapter where they talked about nitrogen and lightning and nitrogen in the soil and then nitrogen in the air with sulfur dioxide converting to sulfur trioxide. This is what they basically like to do. Just put in a bunch of AS topics in a P4 paper just to confuse those students who only revise the A2 syllabus and not the AS syllabus. They just sometimes like to do that. Okay, so you have what the question is telling us. Let me explain it. You have sulfur dioxide, which has two ways to convert to sulfur trioxide. Method number one, react with oxygen to make sulfur trioxide. The problem with this method is it's really slow. So, how can we increase the speed? Use NO. Now, tell me the name of the substance. What is the name which we call a substance which helps to speed up a chemical reaction? If your answer is catalyst, you're right. A catalyst is a substance which speeds up the chemical reaction. Now, question number two, is a catalyst used up in a chemical reaction? No, a catalyst does not participate as a reactant. It does not participate as a reactant, which means that it is going to be the same form as it started the reaction in. So, technically, even if you see some reactions or some examples where the catalyst is being used up or converted to another form, 100% it's going to be converted back to the original form. So if a person looks at the start of a reaction and the end of a reaction, it's going to be the same. Let me give an example. So even here, you just need to remember these two reactions. That first NO, which is your catalyst, reacts with oxygen in order to form nitrogen dioxide. Just balance this: one nitrogen, three oxygen, and two oxygen. So obviously, we put a two here. When you put a two here, we balance the nitrogen first. Now look at how many oxygens are there: four. 2 and 2, 4. That's balanced. Nitrogen monoxide is the catalyst which converts to nitrogen dioxide. Now, if some of you are confused that didn't I just say that a catalyst is not supposed to change its form or is not supposed to participate in the reaction? Yes. But then why is it participating here? I said that a catalyst is not supposed to change its form and it's supposed to remain in the same form it started with at the end of the reaction. And we're going to see that exactly happening. Just a second. Now, once we made this nitrogen dioxide, it's going to chemically combine with sulfur dioxide to form obviously sulfur trioxide. And because it's a catalyst, should we get NO back? Yes, we should. Now imagine this. If a person looks at this and this, he does not look at what happened in the middle. Does the form of the catalyst change? No. Technically, yes, it changed, but it is regenerated at the end of the reaction. So, explain the role of NO and include chemical reactions. You're simply going to write that nitrogen monoxide acts as a catalyst. Now, you could give two reasons for it. The form of nitrogen monoxide does not change technically, or in basic words, you could say, since it is regenerated at the end of the chemical reaction. At the end of the chemical reaction, and then include chemical equations in your answer. Obviously, you need to remember these two chemical equations and the balanced one: 2NO plus O2 makes 2NO2, and then 2NO2 plus SO2 makes SO3 plus NO. Let me just confirm for a second, if double check if both of these are balanced. This is balanced because 2 plus 2 is 4, and then 2 times 2 is 4. Let's look at this. Oh, there's a problem here, right? Two nitrogen and one nitrogen. So I think I added this by mistake. Let's just remove this and see what happens. One nitrogen, one sulfur, four oxygens. Yeah, perfect. That is our answer writing. And that is the end of question number